Welcome to lesson number 2, the evolution of numbers. In the first part of this lesson, we are going to talk about how numbers came into being. It's a very long and fascinating story. We'll just give a little synopsis. In the second part of today's lesson, we're going to look at the different types of numbers that exist today, and more specifically, the types of numbers that will occupy us throughout this course. In algebra, I think you know, we will be using letters like A, B, C, and X, Y, Z. We'll also be using some numbers. But when we use letters, variables, we need to know what type of numbers they denote. So we want to be clear on that, which is why it's very important in an algebra class to set the time aside to review number sets, and that's this lesson. So we're going to use several words in the process of this lesson, and they are, number 1, enumeration, number 2, numeration, number 3, number 4, numeration systems, and number 5, number systems. Hopefully, by the end of this lesson, you'll be able to differentiate among those different words or phrases that seem perhaps all the same to you at this point. Let's start with enumeration. Enumeration is the process of matching objects that you want to count or keep track of using other objects like pebbles, dry seeds, stones, notches that you would cut with a knife on a stick, or body parts. I'm talking about really way back in time when people wanted to count, like a shepherd would go out and would want to know if at the end of the day all his sheep are back and none was lost, or a merchant wants to compute how much money or how much merchandise was sold. Well, how were people counting before there was language? Well, it was like I said, they would do a one-to-one matching with each animal. They put a pebble in a bucket, or would count on body parts. That's the oldest way. So one would be the left little finger, then the ring finger, and then the middle finger, and the index finger, and the thumb. So what would number 8 be, for example? Without any words, it would just be 3, 4, 5, wrist, elbow, shoulder. And without even saying it, it would just be touching these body parts with the right hand or the left hand. That was the first stage. Then when language came about, numeration came into being, and that's the second phase. And numeration was counting the objects, be they people, be they objects, be they money, be they animals, whatever it was that people needed to count, because prehistoric man, even before language, needed always to count. Language came into being, and suddenly it became natural to name the things that they counted. So number words came about. Our number words today are 1, 2, 3, but it wasn't like that from the beginning. The words were, naturally, the body parts. So it was little left finger and the left ring finger and the left middle finger. So number 4 was the left index finger. Number 5 was left thumb. Number 6 was left wrist. So if you look at the old dialects, that's what you find, that the first number words were body parts. So that's numeration. Language pushed forward the evolution of numbers. But in these first 2 phases, which are very old, what's very important to realize is that the numbers were not independent of the objects counted. So when there were 5 objects, for example, there was no concept of the number 5. They were just the 5 objects, 5 sheep, 5 people, 5 whatever. Then came number. The concept of number was a big step forward. It's not clear from history, because we don't have enough information and research has not been able to determine when number first came into being, the concept of number. But it was clearly present in many of the great civilizations. We can see it in Egypt, in India, in Mesopotamia, in ancient Greece. And why do we know that they had the concept of number clear? Well, because we can find in their documents questions like how many? How much? Problem-solving questions. Well, what is the answer to how many or how much? Some ordinal number. So I'd like to pause a little bit about these numbers because I want to say some things about the concept of number which you perhaps take for granted because numbers are all around us. When you get up in the morning, for example, you look at your clock. That might be one of the first things you do. There's a number to denote time. You go in the kitchen. You maybe put something in the oven. You turn on the temperature, 350 degrees. That's a number. You might put something in the microwave. You time it. That's another number. You think about going outside. How cold is it outside? Temperature, another number. You get in the car and you drive. You look at your speed. You're going at a certain speed, another number. You don't want to go too fast because you get stopped by a cop. You want to go somewhere. Your destination is usually somewhere that has an address. An address is a number. You go into a store and you buy something. The cost is a number. You come home at night, you might turn on the TV. The channel is a number, and so on. We are invaded with numbers and we take them for granted. But in the olden days, way back in time, numbers were not as common as today. So what I wanted to point out about numbers is, number one, is that it is not something natural. It is not something that exists in nature. It is not an object or a thing. There is no other animal population that counts or uses numbers. Number is an invention of the mind of man. Number is a creation. So while it's the most natural thing for you, because of the list of numbers I just gave you, and there's so many more that abound in our everyday life, it is also simultaneously the height of abstraction. And what do I mean by that? Well, think about 2 students, or 5 classrooms, or 4 books. And now forget the students, forget the classroom, and forget the books. Just keep the number 2, 4, 10, 6, whatever number, and detach it, disconnect it from the objects that it is counting. That's number. It's abstraction. When you think of 3, you think of a set of 3 things, but doesn't matter what those things are. We just have the abstract concept of number. Well, this abstraction is much more in the more recent history. It's not way back in time. So that's a few things I wanted to tell you about number. Then that brings us to the fourth phase, which is numeration systems. Once the concept of number became a natural thing, then the history of number became a history of numeration systems. But what's a numeration system? A numeration system is some form of way of a mechanism of writing numbers. Now, why did the need for a numeration system arise? Well, if they were counting with pebbles or body parts or dry seeds or whatever, and they got into very big numbers, at some point, your counters, your pebbles, run out. They're exhausted. So we need some form of abstract way using symbols to write numbers, especially big numbers. So the answer was the creation of several different numeration systems. And I'm sure you know about a lot of them. There was the Roman system. There were the ancient Egyptians. There were the Babylonians. There were the ancient Greeks. I mean, there's so many numeration systems. Let me pause and show you something about the Roman numeral system, because I'm sure you've learned that. And then we'll talk about the only one that survived, the one that we use today. Let's go to the whiteboard to do that. You might know that M for the Romans was 1,000, D 500, C 100, L 50, a capital X 10, a V 5, and an I 1. So how would they have written 1001? Well, that would have been an M for the 1,000 and I for the 1. 1001. How would they have written 868? Well, it would be 500 followed by 300s, C, 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 that's 800. 60 we can make with a 50, which is the L, and a 10, which is the X. And then 8 was a 5 and 3 ones. Well, I think you can see how this is a bit cumbersome. I'd like to make 2 points. Number one, in our present numeral system, and we'll talk about that in a second, notice that this number is larger than this one, so its name, its list of symbols, its string of symbols is longer. If a number is shorter, it's smaller. If it's longer, it's bigger. With the Romans, look at this. 1,000 would just be the M. 1,001 is M and an I. And this number that's smaller is so much longer, so it's very cumbersome. Another point is, in any Roman number, these different symbols always mean the same. In other words, this will always be a 1, the X will always be a 10, this will always be a 500, and that will always be 1,000, etc. But let's look at our number system, our numeration system that we use today. Here I have a number, and I specifically picked this one for you, which has 2 same symbols on the outside and 2 on the inside. This symbol here, which is the 1 digit, means a 1, but over here it doesn't mean a 1, it means 1,000. And 0 here means 0 tens, and here it means 0 hundreds. So these digits, while they're the same, these 2 and these 2, they mean different things. So a 4-digit number, we can generalize in this numeration system we use, whatever digits over here represents 10 to the 0 power. Whatever digit is here represents that many 10 to the 1st power. Whatever digit is here is that many 10 squared or 100s, and so on. And the 4th position from the right would be 10 cubed or 1,000. So we have a system today which is called a positional numeration system, where the position of the digit means something very specific. And who must we credit for this positional numeration system? The Hindus, the Indians from India. In the 5th or 6th century, they came up with this brilliant idea. They also are the inventors of 0. It took forever to be born, and though it's the first number of the positive numbers, or whole numbers, it was the last one to be born. And then in the 8th, 9th century, the Arabs translated the work of the Indian mathematicians into Arabic. One of the famous Arab mathematicians was Al-Khwarizmi. And his books, thanks to his books, all of this knowledge penetrated Europe in the 12th century because of the translations back into Latin. So it was first in Hindu, then in Arabic, and then in Latin. So the Middle Ages, by the Middle Ages, all of Europe was discovering this positional numeration system. So there was the war between those who were still using things like an abacus to compute and then write it down, and those who were just using the algorithms that you learned in primary school, how to add numbers, how to subtract, how to multiply, and how to divide. An algorithm is just a procedure that we learn to compute. And where does the word come from? From the Arab mathematician Al-Khwarizmi. That's what an algorithm is. It's a procedure. So when you think about the numeration system we have today, it took a long journey. It started in India, then it went to the Middle Eastern Arab world, then it went to North Africa, and then it went to the Moorish Spain, the Arabs that populated Spain at the 11th, 12th century. So today we have this wonderful invention that we take for granted. There are also other cultures that use base 10 systems. The only difference, and you could look into it, the Chinese, for example, the only difference is they have different symbols. We have the 0, the 1, the 2, up to the 9. They look different, but they mean the same thing. Well, that gives us the first part that led to computation. We now know how numbers came about, how algorithms came about, how computation came about. And little by little, we didn't need objects and pebbles and an abacus or anything like that. We just used the numbers themselves with an algorithm to compute. But in elementary mathematics today, when we learn mathematics, there's another thing we learn, and that's the 5th word of that original list I showed you, and that is number systems. What's a number system? A number system is a set of numbers, and there are different number systems. Counting brought about the first one, and those are the natural numbers. So that's the first set I'd like you to know. Natural numbers are the positive whole numbers starting with 1. It is natural to count 1, 2, 3, 4, 5. That's why they're called natural numbers. So on the next graphic, You're going to see the definition. The set of natural numbers is our first set. The set is denoted by capital letter N, and you notice that the N is a little thick on the left side, and that's to differentiate it from any other capital N. That's the international notation for the natural numbers. And N is the set of 1, 2, 3, 4, all the way out to positive infinity. There are two new symbols there I'm using. The braces are used to denote sets, and that line down 8 is called plus infinity. The next set would be the set of whole numbers. The set of whole numbers in English means all the numbers we just saw plus 0. Now I'm going to call that set W, but it is not an internationally accepted notation, so we're going to put it in quotation marks. So that's set number 2. The set of whole numbers, we shall denote it as the set W, and W equals the set of 0, 1, 2, 3, 4, all the way out to plus infinity. Notice that N, the naturals, is a subset of W, and we write that N subset of W. It looks like it's a new symbol. You might or might not know it. Or we can also write that symbol backwards and say W contains the set N. And we can write that in a Venn diagram with N inside of W. And the only number that W has that N doesn't have is 0. So that gives us our first two sets. How did the third set come about? Well, I'm going to show you with a little equation, because usually in mathematics, when we think of the evolution of things, it was always because of need, because they had to solve problems, or because they had to answer questions whose numbers didn't exist. The answers could not be answered with numbers that already existed, so they pushed the limits and created more numbers. So let me show you an equation that would not have a solution in the whole number system. While we haven't done equations yet, we can still understand these because they're very simple. What number x minus 3 would give me 1? If this is new for you, you can think about it this way. What number minus 3 would give me 1? Well, I think we can guess very simply that the answer would be 4. So there is a solution to this equation, x equals 4, in the whole number system or in the natural number system. What about this equation? X plus 3 equals 0. Well, I think that you can guess, again, that the answer would be a negative 3. But negative 3 is not an element of W. Now, this is a new symbol again. This means to be an element of, or to belong to a set, or to be a member of the set. When you cross it, it means it doesn't belong to that set. Negative 3 is not a whole number. Negative 3 is not a natural number. So we need new numbers. We learned two things from this example. Number one, that the solution to an equation is not something absolute. It's something relative. It depends on the universe of numbers we're working with. And the second thing we've learned is we have to extend our set of whole numbers to include negative whole numbers. And that brings us to the next set of numbers, which is our integers. And here we are, the set of integers. That's the word for them. The set is denoted by capital Z, and that's an internationally accepted notation. And Z is defined by the set of all negative numbers, whole numbers, starting with negative infinity, dot, dot, dot means all the numbers all the way up to negative 3, negative 2, negative 1, 0, 1, 2, 3, all the way out to positive infinity, always taking the whole numbers. W, which is the previous set, is a subset of this new set Z, or we can say that Z contains W. And to show that, we build a larger set around another Venn diagram. So we have Z on the outside, containing W on the inside, and containing N all the way inside. Once again, the set was not large enough. There were still some problems and some questions that could not be answered with positive and negative whole numbers. which are now called the integers. Let's look at what type of problems or questions could not be solved with these numbers. Back to our whiteboard. Our first simple equation says that 2 plus x equals 1, or 2 plus quantity equals 1. What quantity is that x? Well, again, being a very simple example, I think you can see or guess that -1 would be the solution. Well, that number belongs to our new set of integers called z. So there is a solution to this set in z, or to this equation. Let's look at the second equation here. 2 times x equals 1. In algebra, we could also write that as 2x. But I'm just emphasizing with the dot for multiplication. Or 2 times quantity equals 1. Well, I think you can guess that one too. If I take 2 halves, I get 1. Another way of writing the half is 0.5. But whether we write it 1/2 or 0.5, the number 1/2, which is the same as 0.5, is not a member of the set Z. Well, what does that mean? That means that we need new numbers once again. And that brings us to our next set of numbers called the rational numbers. And here's their definition. The set of rational numbers, that's the word for them. The set is denoted by the capital letter Q. That is again an internationally accepted notation, so we don't put it in quotes. I'm going to define this in two different ways. First in English, so the next visual shows you Q equals the set, and that's denoted by the brace, of fractions a over b, like the 1/2 we just saw, such that a and b, numerator and denominator, are integers, and b cannot be 0. The numerator cannot be 0. Well, if I take that English sentence and write it with symbols, it can be rewritten as Q equals the set of a over b, such that, is that slash, a and b are members of z, belong to z, are elements of z, comma, such that b is not equal to 0. Why can the denominator not be 0? Check it. Divide 5 by 0, 4 by 0, 10 by 0, anything by 0, and see what you get. You get something nonsensical. Your calculator will say error. That's because the denominator being 0 times anything would give me 0 and would never give me back that numerator. Well, in our process of numbers here, number sets, we had n, then w, then we had z, now we have q. The question is z a subset of q? Are all integers rationals? Let's go back to our whiteboard and check. Is z a subset of q? Meaning, are all integers, numbers that belong here, also rational numbers? Do they also belong there? Well, integers, I have three types. I have the positive integers, the negative integers, and 0. Can I write 2 as a rational number now that you know the definition? Can I write it as a fraction of 2 whole numbers? Certainly. The simplest way is 2 over 1. That's always the answer. But I also can write it as 4 over 2. I can also write it as 10 over 5. I have 100, 1,000 ways of writing 2 with 2 whole numbers. So yes, 2 is an element of Q. When a set belongs to another set, we use the inclusion sign. When an element or member belongs to a set, we use a little line in between. That means is a member of. Does 0 belong to Q? Certainly. I can write 0 over 1. I can write 0 over 2. I can write 0 over 3. I can write 0 over any positive number, and I get 0. That's not like having zeros at the bottom, which I mentioned earlier. If zero's at the bottom, it's undefined. If zero's on top, you get 0. Try it and divide and figure it out. You know the algorithm. So yes, 0 also belongs to Q. Finally, a negative number. I can always write it -5 over 1, but I can also write it -10 over 2. I can write it as -20 over 4. These are whole numbers. Sorry, they are integers, positive or negative whole numbers, so you also have here an element of Q. Therefore, all integers are rationals. We have a next result. Z is a subset of Q. Indeed, Z is a subset of Q, or Q contains Z. And now the picture, the Venn diagram, gets even bigger. We have an N on the inside, contained by W, contained in turn by Z, and finally contained by Q. Before we go to the last set of numbers, I'd like to ask a question, a little digression here. What is the form, the decimal form of these rational numbers? I urge you to take your calculator and divide a lot of whole numbers, A by B, an integer by another integer, and see what we get. Let me show you the different types of answers we get. Back to our whiteboard. Here are some simple ones that you know: 1/2, -3/4, 8/5. If you were to divide numerator by denominator, you get numbers, decimals, that end after a certain number of digits. These are called terminating decimals. There are others in the same set of rational numbers now, the set Q, where you have again an integer over an integer, plus or minus, it doesn't matter, where when you divide it out, you get things that repeat. Here, 2/3 is 0.66666 out to infinity. We write that this way. The little bar means that this digit repeats itself. 6 is the period of the number. In this case, 45 keeps repeating itself. 45 is called the period and denoted by the bar. This number has a long period, has a 6-digit period. That means that this number here, a rational number, when divided, gives a decimal that has a decimal form 2857714, 2857714, on and out to infinity. So we can conclude another result, but you should compute a lot more before you accept my result. A rational number is either a terminating or a repeating decimal. Well, weren't these numbers enough? Weren't these numbers called rational numbers that contain all the previous sets enough to answer any problem or questions whose answer was a number? No, we needed more numbers. And let's go to one last equation. Back to the whiteboard. What number squared gives me 4? You know that answer, 2 squared or -2 squared. The answers are integers. What number squared would give me 1/4? Well, 1/2 and -1/2 would be the answers. These numbers are rational numbers. But what about this equation? What number squared would give me 2? Well, you know that today because it's easy to get a calculator, take the square root of 2, and find this decimal. If you then square this decimal, you would get 2. So the answer is this number. But at that time, when they only knew about rational numbers, this was a weird number, a strange number. What's strange about it? It has no pattern that repeats itself, so it has no period, and it never ends, even though on your calculator it comes to an end because your calculator has a certain width to it. Therefore, irrational numbers, these are new numbers, irrational are numbers that are decimals that never end and that don't have a period. So they are not rational. So they don't contain the rationals, they are apart. So our last visual shows you the sets that we had before, which are Q containing Z containing W containing N, and on the right of it we have I, the irrationals, such as square root of 2, or square root of 3, or square root of 5, or pi, or phi, that we will visit later on in this course. I is not an internationally accepted notation, so we put it in quotation marks. Together, this entire system is called the real numbers, and we bring in a final new letter. Capital R are the real numbers. They contain the rationals and the irrationals. And it is the real numbers that will occupy us in this course. One last activity I want to show you. How did the ancient Greeks first encounter radical 2, square root of 2, and they realized something was strange? Let's go to the whiteboard. Here I have 4 square units. The side of each square is 1, and they're divided into 2 pieces. When the Greeks wanted to know what number square would give 4, they actually made a square whose area was 4. Putting that together, it gave them a square whose side length was 2, and that's the positive answer to that equation, 2. Now what about a square that gives me 2 square units? Here are my 2 square units. How can I make a square that equals 2? Again, the positive lengths. Well, they were very ingenious, turned these around, and made a square whose area totals 2. And that's when they found out that it was the hypotenuse of a right isosceles triangle whose legs each equal 1 and whose hypotenuse equals the square root of 2. So the square root of 2, called radical 2 when we're looking at the positive, and radical 3, or positive square root of 3, and all the other ones that are not the perfect ones like square root of 4 or 16 or 25 are the irrational numbers, along with pi and others that we'll visit. So what you need to remember from this lesson is that the real numbers is the set of the rationals together with all the irrationals. That's the set of numbers that we will work with.